Okay, so this is section 4.1, part 2. We're going to talk about the natural base. It's called this because it occurs in a lot of natural applications. This is base E, where E is an irrational number like pi. It's about 2.71828. And it is irrational like pi. To remember, is approximately 3.1415926, so on. E is the same type of number. All right, so with that said, E behaves the same as the other bases. So all the stuff you learned for the other bases on the previous section is still going to work on this one. For instance, it goes through the point 0, 1. And this thing, by the way, is written as e to the x is the parent of this guy. So it goes through 0, 1. It's got a horizontal asymptote. At y equals 0. Domain is going to be all real. Range is going to be y bigger than 0. However, e to the 1 is 1e. So at point 1, your y value should be something a little less than 3. And e to the negative 1 then will be 1 over e. So it will be a little bit smaller value. So this guy will not fall nicely on an integer because it's irrational. The transforms also work the same. Okay, so let's go in and start talking about some applications. The first one let's talk about is money. Believe it or not, this falls under it. Okay, so if you've got some principal, which is the amount of money you're originally going to invest, you're going to compound it, which means you're going to add interest into your account in times per year. And compounding means the number of times that they add interest into your account. T is the number of years you're going to invest at. And R is your rate you're going to invest at. As a decimal, not percent. So if we're compounding something, for instance, then the amount of money you're going to have after T years will be your principal times 1 plus R over N to the NT. We talked about this in Algebra 2. Okay, where this again is the amount you start with. This is the rate as a decimal. This is number of times per year you're going to compound it. And this is how long you're going to leave it in. You plug these things in, and you're going to get the amount of money you will have. Now, if you're compounding continuously, and this is for discrete time periods, but if you're compounding continuously, It's a little bit different. It's still P, except now it's E to the RT. And you just plug these things in. Let's work in an example. So let's say we have $1,000 we're going to invest at 3% interest for 10 years. So you've got to choose between two accounts. One compounds monthly and one continuously. But they've got the same rates. So let's see which one's going to be better. Well, first thing we do is go back in. So A of 10 equal to 1,000, that's the amount we're going to start, times 1 plus, we're going to start with the compounding monthly. So my rate is 3%, which is 0.03. Compounding monthly is 12 times a month, times 12, times 10. And then you go in and you calculate that. And we end up with $1,349.35. You're dealing with money, you should always go to 2 decimal places since that's pennies. So now let's do, and this is monthly. So now let's do continuously. So A of 10 will be equal to 1,000 times E to the 0.03 times 10. And we end up with $1,349.86. So as you can see, there's not a tremendous amount of difference. This one is going to give you 51 cents more than the one compounded monthly. Okay, so now let's look at another example of stuff that works out. Radioactive decay. And let's say we're looking at the equation we're given is 13 times e to the negative 0.015 t. All right, this is the amount you started with. This is the rate of decay. And we know it's decay because of the negative. All right, so what we want to do with this is find how much remains after 45 days. So on this one, all we do is we plug it in. So m of 45, which is the amount of mass after 45 days, equal to 13 times e to the negative 0.015 times 45. Plug that in your calculator, and it works out to be around 6.62 grams left. So we're almost half of it there. So 45 days is not going to be exactly our half-life, but it'll be pretty close to it. Okay, the other application you're going to see a lot of for this is in biological populations. This is usually given by the logistic formula. And this is usually shown in most introductory freshman biology classes in universities. And the logistic formula typically looks something like this. So population at time t is going to equal to P sub c. This is what's known as your carrying capacity. It's how many of these little critters the environment can hold, divided by A plus B e to the negative RT. A and B are population parameters. And R is your rate of increase if it's positive, or decrease if it's negative. Okay, so let's look at an example of this. But this is basically the logistic formula right here. So in this formula, we know that our carrying capacity is going to be 1,200. In other words, we really don't think that the population is going to be able to handle much over 1,200 of these guys. A is 1, B is 11, and R is 0.2. The first thing you want to find out is how many were originally in the pond. Okay, well, this is relatively easy. Here t is 0. So we're going to plug into our logistic. The population at time t will be equal to our carrying capacity over 1 plus 11, and here I'm plugging in what I've got, times e to the negative 0.2 t. We plug all of these in, so P is 0, then it'll be equal to 1,200 over 1 plus 11 times E to the negative 0.2 times 0. Okay, now anything to the 0 is 1, so that's going to give me 1,200 over 1 plus 11, which will be 100. So we started out with 100 fish in this thing. I want to figure out how many after 20 years. So again, we just plug in P of 20 is going to equal to 1,200 over 1 plus 11 e to the negative 0.2 times 20, which gives me 998 points, I think it was 75 fish. 98.775 fish. And don't give me that as an answer. Don't give me part of a fish. Round it up. You're going to have 999 fish in here. Do not do parts of a fish.